What's going on, everybody? It's Mr. Gus, and I'm in the physics conference room today. We're going to talk about drawing E-field lines. So drawing E-field lines are one of those ways we can actually start to model an electric field. We can start to model the amount of force felt by a positive test charge near things, but also it helps us understand maybe where equipotential lines are, things like that. So drawing electric field lines, I've got a few examples today. The one thing you have to remember is that an electric field line, by convention, points in the direction that a positive test charge would go. So as I'm drawing these things, we're always thinking in our brains, where would a positive charge go if I popped it right there? If you can figure that out, then you know how the E field is drawn. Let's try an example, okay? So first things first. Over here, I've got a charge of, this is poorly drawn, I've got a charge of positive Q over here. I got a charge of negative Q over here, okay? Let's think about this. If I were to put a positive charge right there near Q, which way would it go? Well, you're right, it would push this way, and that's pretty easy to draw, right? What about this? What if I put a positive test charge up here? If I put a positive test charge up here, well, it would push away from this charge, but it would be attracted to this charge. So it would kind of get pushed away and then pulled back down over here as it starts to take over. And so we can start to try to like fill these lines in, right? Positive test charge down here, it's going to get pushed away in this direction, but attracted in this direction. So we're going to see it push and pull this way. Now, what if I had a positive test charge out here? If a positive test charge is out here, well, this pushing from the positive charge and this pulling from the negative charge, the pushing from the positive charge is going to kind of take over. So I'm going to kind of see this thing radiate out this way. But then as I put these points here and here, it's going to get pushed away until at a certain point it's going to get pushed back around over here and pushed away until it gets wrapped around over here. And if I think about test charges over here, well, these test charges are going to just get pulled right in. So I'm kind of seeing, this is generally speaking my E field around 2-point charges. Right? I've got this positive test charge, positive charge, negative charge, and they're both interacting. They're kind of producing this kind of field, and you can kind of draw these lines in the middle here and here to fill those in. Now, the density of those lines, how many lines we draw, is directly related to the strength of those charges, okay? So if this was twice the charge, you'd see twice the charges emanating from it. And if this was twice the charge, you'd see twice the amount of electric field lines entering it. And that's just kind of convention, but it helps us understand that if those charges are larger, they produce more force. Again, E field is a measurement of force per charge felt on some test charge. Let's try something a little different. Other than point charges, we have plates, parallel plates. This is a parallel plate. Let's imagine a point P right there. That's a point. Which way, if that charge is positive, which way will it feel a force? Well, it'll feel a force directly away from this plate towards this plate. So these parallel plates produce E fields that are perfectly horizontal or perfectly parallel, I guess perpendicular to the plate. Okay, we talked a little bit about voltage or equipotential lines running this way. Well, E field lines and voltage lines are perpendicular to each other. Okay, there's a difference in potential. The difference in potential produces a force this way. If I'm on the same voltage line or equipotential line right here, there is no force pushing between these points. That's why there's no work down there. It's a different idea, but this is how we would draw these E field lines, always in the direction that a positive test charge would go. This is going to be crazy. Not really, it's kind of a physically question, but difficult. What about this? What if I have something like this, where there are two different positive plates here? Well, let's imagine a test charge, say, right there. The test charge is here, closer to one plate than the other. We know it's going to feel a repulsion from this plate and this plate, but definitely more so from the one on the left because that point is closer. So we're going to say it's going to get pushed away, but as it gets pushed away from here, it's also going to get pushed away from here. So we're going to see this like pushing back and forth a little bit. And so there's actually like an infinite electric field in here, I think. It's going to be like this weird push and this weird push up and out and push and push. And so we're going to see this pushing back and forth, right? There's definitely an E field here and here and here and here. And as we get closer to the middle, in the middle, that force is going to push back and forth until it pushes itself outward. So we see this like outward pushing electric field. Now, as we go up this way, the E field kind of continues to push away, 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 up, away, away, down, away, away, away. So between this field, it's kind of the exact opposite, inverse of this. There's a clear electric field here. In terms of positive test charges in here, this thing is getting pushed away as hard as it can, right? Put a test charge here, it's going to push away until it can't really go anywhere else. We get this kind of constant pushing away from there, okay? Let's look at a different example. This time, we're changing it to where I have a positive 2. There's much more charge, double the charge here than there is here. So because there's double the charge, it will experience, or it will provide, double the electric field over there. So let's think about a positive test charge. Let's put a positive test charge down here. There's a positive test charge down here. Well, it's going to experience a little force from this positive Q, but it's going to experience a double force from right there. Okay, so I need to make sure I'm going to see this kind of like downward. This is my force vector diagram, right? Like I'm adding this vector to that vector, so it looks like this is actually going to point in this direction. So radiating out. So instead of having this kind of like in the center, this area of really strong electric field in the middle, we're going to see that charges are actually going to point, these field lines are actually going to point and kind of converge, I guess, or start to diverge really closer to the positive charge, the positive 1 charge, not the positive 2 charge, because this is providing a much larger, specifically a double the force compared to the other charge, okay? Now, another convention we can do is make sure we have double or many more field lines leaving this charge than this charge. Let's see, I got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's just add a 16th to make it exactly double. So I've got 16 field lines leading here. I've got 8 leaving here. And look, this like gap in field lines is closer to the weaker charge. That's because this has a greater force. A test charge here would get pushed closer to that charge. We have one more. This is a 3-body system. In physics 1, we talk about 2-body systems. This is a 3-body system here where I've got a double charge down here, I've got a single positive charge over here, and I've got a single negative charge over here, or 1Q, let's say, okay? So let's think about a test charge. If there's a test charge located right here, closer to 2, it's going to feel a very large force pushed this way, but eventually, as it moves this way, this charge is also going to push it away. So we're going to see that there's a great force until it reaches a distance closer to Q, like we saw last time, and then it's going to push away this way. Test charge here, push away this way. Okay, so the same field lines getting less extreme as you get closer. Now, when we think about test charges on this side of the picture, over here, we're definitely going to be pushed away from the positive 2 Coulomb charge, positive 2Q, pushed away from the positive 1 Coulomb charge, but we are attracted to this Q over here. So we're seeing this attraction over here, a really, really strong attraction over here. And it really, again, test charge, pushed away from here, so pushed, but then attracted up here. So we're seeing this kind of attraction over in this direction right here as well. Okay, so kind of pushed away, pulled towards over there, this way, and then obviously radiating out this way. Many, 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 many more field lines drawn out of the positive 2 charge. And then we can even draw some field lines entering from over here. So we're seeing again, where is this middle point? This middle point should be pushed up this way, pushed closer to this, but then also we're seeing field lines going this way. So if we have to analyze a model of this, we're kind of analyzing where are how are the density of field lines different here compared to here. That'll tell me the magnitude of that charge. How are the field lines different here and here? Are they going towards or away? So big takeaways of this. Field lines enter positive charges. They leave positive charges. They flow in the direction of a positive test charge, and then the density of those field lines indicate to us the strength of that field, or the strength of the charge producing that field. Dense lines, higher E field, higher charge. Flow away from positives and towards negatives. All right, you got questions, comments, email, ask me in class. Till next time, see ya.